Welcome to another edition of our class on mathematical method. In our former class, we discussed Legendre equations and polynomial. We look at the general form of Legendre equation. We obtain the Legendre polynomial, which are the solutions of the Legendre equation using the method of Frobenius. We emphasize on the structure of Legendre polynomial of first kind in that class. Today, we shall continue with Legendre equation and polynomial by considering some examples. Once again, you are welcome to today's class. I am Ablegeni Ridwanullah Inyoda. In our previous class, we told ourselves that the general form of Legendre equation is 1 minus x squared y prime prime minus 2xy prime plus n plus 1y equals to 0. And that one of its solution, Legendre polynomial of first kind, is given as 1 multiplied by 3 multiplied by 5 up to 2n minus 1 divided by n factorial into bracket x to the power n minus n into n minus 1 divided by 2 multiplied by 2n minus 1 x to the power n minus 2 plus n into n minus 1 n minus 2 n minus 3 divided by 2 multiplied by 4 multiplied by 2n minus 1 multiplied by 2n minus 3 minus it continues. So today we shall be considering some examples on the Legendre equation in general and some example on Legendre polynomial in particular, the polynomial of first kind. So let us take some examples. So examples. Number 1, with the aid of the substitution x equals 1 plus t, comma, show that the solution of the Legendre equation (1 minus x squared y prime prime minus 2xy prime plus n into n plus 1 y equals to 0) from the first principle, is Pn of x equals f into minus n comma n plus 1 semicolon 1 semicolon minus t divided by 2, where f is a hypergeometric function. Full stop. Now let's look at this question very well and analyze. We want to make use of the substitution x equals 1 plus t. The second one is we want to establish relationship between the Legendre polynomial and hypergeometric function. Don't forget that we have discussed hypergeometric function in one of our previous classes. And we are to establish this from the first principle, that is the definition. And what is the first principle in this case? We are to establish the relationship between the Legendre polynomial of first kind and hypergeometric function given by what we have at the right hand side using the method of Frobenius. To do this, let us solve the problem. Now, the Legendre equation 1 minus s squared d square y dx squared minus 2xy 2x dy dx plus n into n plus 1y equals 0. Let us call this equation 1. Now our substitution, x equals 1 plus t, that's what we have. Then automatically the x dt becomes 1. Call this one equation 2. So from equation 1, what we need is the y dx, not the x dt. So how do we obtain that? We write the y dx equals the y, the t, multiplied by the t, the x. And this is what we refer to as chain rule from elementary calculus. So let us substitute the t dx into this expression. We have the y, the x becomes the y, the t. Call that one equation 3. Now our second derivative, the square y dx squared, will have been d dt of the y dt multiplied by the t dx. Unfortunately, the t dx is 1, so the derivative of the y dt will give us the second derivative of y with respect to t. And that becomes the square y dx squared equals the square y dt squared. Call that one equation 4. We now substitute equation 2, equation 3, and equation 4 into equation 1. Using equation 2 to 4 in equation 1, comma, we have. What are we going to have? Let us substitute this value here. By the time we open, we are left with minus 2t minus t squared d square y dt squared minus 2 into 1 plus t. The y dx is the y dt plus n into n plus 1 y equals to 0. So we can decide to multiply all through by negative to cancel out the negative, or we maintain what we have. So let us call this one equation 5. Let's call the resulting value equation 5. Now, we now make use of the first principle as contained in the question from equation 5. And what do? We let our trial solution to be summation AR, then the variable of the problem now as transformed from x to t, so that becomes t raised to power r plus c, r from 0 to infinity. Call this one equation 6. So we now substitute equation 6 into equation 5 now. So how do we do that? We have minus generally on that. So differentiate this one twice and substitute here. We are going to have 2 summation r from 0 to infinity r plus c minus 1 t multiplying will give us ar t raised to power r plus c minus 1. Then this become plus, since I have factored out the negative there. We have this one to be summation r plus c minus 1 ar t raised to power r plus c, r from 0 to infinity. So we are done with this, with the term with derivative. The next one is minus 2 summation, let me open bracket there, 2 is multiplying, 1 multiplied by the derivative of equation 6 will give us r plus c ar t raised to power r plus c minus 1 r from 0 to infinity, then plus t multiplied by that, the first derivative of equation 6 gives summation r from 0 to infinity. We have r plus c ar t raised to power r plus c plus n into n plus 1 summation ar t raised to power r plus c r from 0 to infinity, everything equals 0. Do not forget that at this point, before we move on, we must confirm the number of terms that is expected. So here we have 2 terms here, 1, 2, 3, 4, 5. We are supposed to have 5 terms in total. 1, 2, 3, 4, and 5. So we are supposed to close the bracket here, then plus. To make it easier, let us factor out the negative, multiply all through by -1, and then collect the same power together. By so doing, if I multiply all through by -1, this negative cancels out, this cancels out, this becomes negative, and we have same power, r plus c minus 1 here, r plus c minus 1 here. Others are r plus c. So let's bring them together under the same summation. For the first one, summation r from 0 to infinity, the negative cancels out here. So we are bringing this and this together. Do not forget they have the common factor here to be r plus c. Bringing out r plus c, we are going to have r plus c squared ar t raised to power r plus c minus 1. That's what I'm going to be left with. Then here, r plus c. If you bring 1, 2, 3 together, do not forget this has become negative because of the multiplication. Then there is a common factor between these two. We're going to have r plus c squared plus summation into r plus c squared minus n into n plus 1 ar x is for t raised to power r plus c, r from 0 to infinity. That is what we have left. Now, hold on. I have not considered the 2 here. This is supposed to be 2. I have not considered the 2 multiplying. So, this is supposed to be r plus c is common. R plus c is common. Then we are left with 2 here plus what we have. That becomes r plus c plus 1. Sorry about that costly mistake. Now, everything equals 0. So, having done this, the next line of action is to look at the difference between the power. The difference between the 2 power is 1. So what we are going to do now is to ensure that we make them the same power. To make them the same power, we focus on the least power. And since the difference between them is 1, we move this one forward, then we return it 1 step backward. How do I mean? Evaluate t raised power r plus c minus 1 at r equals to 0. We have 2 r equals to 0 c squared a naught t raised power c minus 1 plus summation r from 0 to infinity. We are going to have twice r plus c plus 1 a r plus 1 t raised power r plus c plus summation r plus c, r from 0 to infinity, r plus c plus 1 minus n plus 1 into n, a r t raised power r plus c equals 0. So we equate the coefficient now. Equate the coefficient. If we equate the coefficient, we assume the first one, the first time there, that a naught is not 0. This implies that our c will equal to 0 twice. That's a repeated root. And since it has 2 repeated roots as initial root, automatically one of the solutions is going to be logarithmic in nature. But we are not interested in the logarithmic solution. We are interested in the second solution that is not logarithm in nature. So let us continue. So here we have the same power t r plus c r plus c. Let us equate the coefficient and make the highest subscript the subject of the formula. The highest subscript of a is r plus 1. Make it subject of formula. We are going to have n into n plus 1 minus r plus c into r plus c plus 1, all divided by twice r plus c plus 1 a r. So what we have now is what we refer to as our recursion formula, recurrence formula. Let's call it equation alpha. Now, let us now substitute our initial root. Let's substitute our initial root into the recurrence formula. when C equals 0, equation alpha becomes, see, it becomes AR plus 1 equals n into n plus 1. I have r minus r into r plus 1 divided by 2 into r plus 1 AR. Let us factorize the numerator. Let us factorize the numerator. What are the factors? The factors are, let's first of all write it as n squared. I have minus r squared there, plus n minus r, which is n minus r into n plus r plus 1. So this gives n minus r into n plus r plus 1 divided by 2 into r plus 1 AR. So let us start substituting for r. So we have A1 when r equals to 0 to become n into n plus 1 divided by 1 times 2. So let's move to the next one, A0. The next one is A2, and that is that r equals to 1. Then we are going to have n minus 1 into n plus 2 divided by 2 multiplied by 1 plus 1 multiplied by 2 A1. There is value for A1 already. And what is that value? We have value of A1 to be n into n plus 1, 1 plus 1 divided by 1 times 2 A0. So substitute that value. We will have n into n minus 1 into n plus 1 into n plus 2 divided by, I have this one to be 1 times 2, 1 times 2 multiplied by 2 multiplied by 2. Something is not right. Oh, this is supposed to be squared. So I will have had this one as 2 multiplied by 1 squared, and this will have been 2 multiplied by 2 squared, which will give us 2 squared dot bracket 1 squared dot 2 squared. Yeah. A0. Let's take one more term before we go to the generalization. A3. What will A3 give us? A3 simply means we substitute 2 for r here, and we have it as n minus 3 followed by n plus 3 divided by 2 multiplied by 3 squared A2, which eventually becomes n minus 1, n minus 3 r is 2, n minus 2 into n plus 1, n plus 2, n plus 3, all divided by 2 raised to power 3 Then I have 1 squared, 2 squared, multiplied by 3 squared, A naught. It continues. What will now be the generalization? It continues in that order. So let us now generalize. Let us start with what we have here before we move to the generalization. We do not have problem with this. N plus 1, N plus 2, N plus 3. Of course, the N plus, that will have been N plus 1, N plus 1 plus 1. Then I have N plus 1 plus 2, which simply defines N plus 1 sub 3. N plus 1 sub 3. Now, let us now look at this. Does it define factorial function? Let's look at it this way. N into N minus 1, N minus 2. Suppose I write it as N. I put minus N here. Let us write this one as minus N. I can as well write this as minus N plus 1. At the same time, we can write this as a minus into minus N plus 2. Oh, this is good. This is interesting. So we have 1, 2, 3, minus 1 raised to power 3 outside here. We are now left with minus N plus 1, minus N plus 2. Oh, that is fantastic. So this now defines factorial function. And that becomes minus 1 raised to power 3 minus N sub 3. That's what we have. So we can write this one now based on this explanation that A3 is minus 1 raised to power 3 minus N sub 3. Then we have N plus 1 sub 3 all divided by 2 raised to power 3. Then I have what we can duplicate this as 1 times 2 times 3, and at the same time 1 times 2 times 3, then A naught. So that A3 becomes minus 1 raised to power 3 minus N sub 3, N plus 1 sub 3 divided by 2 raised to power 3. The first one I can take it as 1 sub 3, while the second one can be taken as 3 factorial A naught. So if we now proceed in that form, we can now make our generalization. And what is going to be the generalization? The generalization there becomes A sub k equals minus 1 raised to power k minus N sub k, N plus 1 sub k, all divided by 2 raised to power k, 1 sub k, and k factorial A naught. So we now go back to our trial solution. Recall that trial solution is y equals to summation a r x to the power r plus c, r from 0 to infinity. So when c equals to 0, we have y equals to summation r from 0 to infinity a r x raised to power r, and that is because c equals to 0. Now, in an expanded form, we have a naught to be an arbitrary coefficient That's an arbitrary value. So in that case, we write y equals a naught plus, from a1 to ak, we are generalize everything. So we have this one to become a sub k x raised to power k, k from 1 to infinity. Now we have this one to be a naught plus our a sub k is minus 1 raised to power k minus n sub k, n plus 1 sub k divided by 2 raised to power k. Oh, sorry, this is t. The variable of the solution is t, not x. So this is going to be t. Then 1 sub k, k factorial. Then we have this one to be t raised to power k a naught. Let's see whether a naught can come into the summation. If it can, then the whole of this expression must give us 1. Once we substitute k equals to 0. Let's substitute k equals to 0. This is 1, this is 1, 1, 1, 1, 1. So eventually this becomes k from 1 to infinity minus 1 raised to power k minus n sub k, n plus 1 sub k divided by 1 sub k, k factorial, then t. That's t divided by 2 every t raised to power k. The minus 1 can also be put together with t. Since they have the same power, law of indices will take its course at that point. Law of indices takes its course there. Then we have y equals to a naught summation minus 1 raised to power k, sorry, minus n sub k, n plus 1 sub k divided by 1 sub k, k factorial into minus t divided by 2 raised to power k. And what we have left defines hypergeometric function. And the solution of Legendre equation of the first kind is given as Pn. So this now becomes Pn of x equals f minus n, comma, n plus 1 semicolon 1 semicolon minus t divided by 2 as required. We can as well make substitution. F minus n, comma, n plus 1 semicolon 1, substituting for the value of t. Do not forget that our substitution was x is 1 plus t, x is 1 plus t. So making t sub a formula here, we're going to have t equals to 1 x minus 1. Substitute that value here, we have the result to become 1 minus x divided by 2. And that is the required result. I want to believe you are all following the class. I know you are very happy now. Please, we'll be able to establish relationship between Legendre equation and hypergeometric, the solution of Legendre equation, which is the Legendre polynomial of first kind, and that of the solution of hypergeometric equation, which is a hypergeometric function. We've seen the relationship between the two of them. In the examiner can ask, establish the relationship between Legendre function, Legendre polynomial of first kind, and the hypergeometric function. In that, the transformation equation will be given. Then you can now follow the process. Let's take another question. Show that the substitution x equals cos theta reduces the Legendre equation (1 minus x squared y prime prime minus 2xy prime plus n into n plus 1y equals to 0 to d theta of sine theta dy d theta plus n into n plus 1y sine theta equals 0. So we want to establish this. It's very simple and straightforward. In fact, this is the relationship between Legendre equation and trig function. Of course, in one of our subsequent classes, we shall look at how they are related per se.